What I'd like to do now is cover calculating risk. And remember, I want to make some important points that I don't want you to forget and I want you to focus on. That statistics match study designs. You heard me say that earlier, and oftentimes people get confused. And then you have to know three table layouts, and I will emphasize those. Otherwise, you're going to come up with the wrong answer. So, um, first point, statistics match study designs, and table layouts match study designs. Okay, so we're going to calculate risk, and we're going to do so for a prospective study. Really, what we're focusing on here is all the observational studies. We're not going to focus on the experiments at all. Those are done usually by biostatistics, using some biostatistics subroutine. But I'll try and be as clear as I can for you as we go along. And of course, the Cadillac study, the prospective study, you calculate the most statistics for it as opposed to a case control study, a historical prospective study, or a cross-sectional study. Okay, now, so when we talk about calculating risks, there are two basic terms to know, and these have to do with direct measures of risk and indirect measures of risk. Okay, so you can see that the Cadillac, the gold standard is a prospective longitudinal study, and it is a direct measure of risk. And which is best? Of course, a prospective study. And which is best, direct or indirect measures of risk? Of course, direct measures of risk from a prospective study are the best. So the indirect measures of risk are connected, and you haven't had this yet, but you can just, for right now, you can just draw a line through that and not worry about matched and unmatched cross-sectional study. But you do know about a cross-sectional study. We've covered it: slice of time, questionnaire, interview, whatnot, and we talked about the pink book and how you could get it. And then we talked about a case control study and a historical prospective study. These are all indirect measures of risk. This is the only direct measure of risk. Now, I mentioned that with a prospective study, it has the most statistics, okay? And with an indirect measure of risk in all these various study designs, we have one measure, one statistic that we do, or one outcome, I should say, because there's two different study designs for the matched and the unmatched cross-sectional study. But you'll see it, and don't let this confuse you. Now, I'd like to talk to you about assessing risk, and remember, we have the most measures of risk for a prospective longitudinal study. Again, that's the best study you can do. That is an observational study. Now, it's one thing that you have to recall and remember, that absolute risk is equal to incidence rate. Now, what makes all these terms difficult is their similarity, and we talked about demic before. I know we talked about wholly endemic, we talked about pandemic, we talked about epidemic, and a lot of these terms are the same, and you always hope when you learn something that they're distinctly different. And frequently when we talk about incidence rate, it is not listed. Absolute risk is. So you have to know that absolute risk means incidence rate. And attributable risk is the amount of risk attributed to the exposure. And preventive attributable risk, it has to do with if people didn't engage in the behavior, how much risk would there be? And then relative risk is a matter of how serious the risk is, and we'll talk about how to calculate that. None of the math is difficult. You're going to add and subtract and multiply and divide. So you're going to use basic mathematical functions. So it's not difficult to do. Now, we could do a relative odds with a prospective study, but we don't calculate an odds ratio or a relative odds ratio because the Cadillac statistic that you get is relative risk. And frequently you hear about this on the radio, and most people don't quite know what it means, but you will, and you'll be able to interpret it. You'll be able to read studies. You'll be able to take in information in your field that reports things according to relative risk. And so, again, relative odds ratio can be calculated, but not done because relative risk is the gold standard. And I want you to also note that all formulas require the use of absolute risk or incidence rate, or the number of new cases divided by the population at risk times K. So that's the same formula you learned from the beginning of class when we were talking about incidence rate. There's nothing new. We're just talking about applications and study designs. Now I want to talk to you about a case control study, which is an indirect measure of risk. I know I'm being redundant, but I'm being redundant on purpose. And the only statistic we can calculate 1, 2, 3, 4 statistics from a direct measure of risk or prospective or longitudinal study, and we are going to calculate one measure of risk from the other observational studies. So if we talk about an odds ratio, also known as the multiplication of cross products, right here, you'll see how quick and easy that is to do. And cross-sectional and historical prospective studies also use an odds ratio, and an odds ratio is similar to relative risk, but it's not as accurate an estimate of risk, and so, but it's the only calculation that can be made from a indirect measure of risk. Okay, so now I want to let you know here, when we deal with cross-sectional studies, there are two types. We talked about matched and unmatched, and you still get an odds ratio from them, but you calculate them in a different way. And there's three tables in their layout that you have to attend to in order to do the correct calculations. Okay, the first one I'm going to start with, of course, you've had enough exposure to these lectures, is I'll peel it like an onion. I'll go right through it one after another, so you shouldn't be confused about it. Now, notice, when we have a prospective study, we have disease develops, right? Disease does not develop because we're following them over time. And then we have exposure, exposed and not exposed. And if we're going to calculate absolute risk or incidence, that's A divided by A plus B, and that's the incidence in the exposed group. And we're going to, all calculations are done with absolute risk. And you can see the absolute risk for the exposed group and how to calculate it, and the absolute risk from the unexposed group and how to calculate it. Now, I have said nothing new to you because you know how to calculate absolute risk or incidence rate. Okay? Now, relative risk is calculated with absolute risk, or the incidence rate among the exposed individuals, and the incidence rate among the non-exposed individuals. So that's information you're going to get from here and here. Now, please take a mental snapshot of this particular table and notice how every one of the cells are labeled, because you're going to need to know that. And remember, the key thing to remember is absolute risk is just another name for incidence rate. Okay? So I'm assuming we're together thus far and you're not confused. Now, attributable risk. This is, I don't know, some people have trouble with this. I'm not certain why, but I'll try and make it as clear as I can to you. And you should not be confused by it, because we've already gone through a problem similar to this, and I will refer to it, and I hope I refer to it in a simple, unconfused way. Some subjects exposed to a factor will not develop the disease. Okay, you can say they have an immunity, right? Or they received an injection. Some subjects not exposed to a factor will develop the disease. Now, I want you to recall how we computed the secondary attack rate for the foodborne outbreak in Oswego, New York, Lycoming, Oswego, New York, and what you observed in the line listing when you began to count cases. If we looked at the first page, most who ate the food became ill. But when you looked at the second page, some people who ate the food did not become ill, right? So some who ate the food became ill, and others who ate the food did not get sick. So you're already used to this kind of thinking, and this is typically what happens, and people get concerned that this means that there must be something the matter either with the study design or the cases or whatnot, and this is just normal behavior with an illness. Okay, now hope you have that firmly in mind and you're comfortable with it. Attributable risk, the amount of risk attributable to the disease. Okay, and attributable risk and proportion of attributable risk for a group. Now, with doing a prospective study, we're going to do group statistics and population statistics. So you have two sets or two different types of statistics to do, and one set of statistics builds on the other. Okay? Now, we've already talked about attributable risk, also known as incidence ratio. So attributable risk, the proportion of a disease attributable to a particular exposure. Let's go over this slowly. For example, in a population of smokers, how much of the lung cancer is associated or attributed to smoking, and consequently how much of the lung cancer could have been prevented if they did not smoke. Okay? So we want to focus on the work group, for example, because we're going to do the same type of statistic again for estimating population risk and ascertain whether our group is representative of that population. And don't worry too much about what I've said. You'll see it unfold before you. And then we'll look at the proportion of attributable risk is also referred to preventive attributable risks. So there's two terms here. So you can think of proportion or preventive attributable risk. Both terms are used for this particular calculation. I use proportion because we're going to calculate a proportion. And we know when we calculate a proportion, whatever is in the numerator is repeated in the denominator. Okay? But this statistic has to do with how many cases or what proportion of disease could be prevented if people did not engage in the behavior. So that's what we mean by preventive attributable risk, okay, or proportion of attributable risk. Now, let's go slowly through these. Now, notice how complicated the statistics are. So, you're going to look at attributable risk. Now, absolute risk, or the incidence rate in the exposed group that is attributable to the exposure. So we're going to take the incidence in the exposed group minus the incidence in the unexposed group, and that's going to give us attributable risk, AR. Now these are group statistics. Just remember that. So we have proportion of attributable risk, and we said this could be preventive attributable risk, and it's a proportion of the absolute risk or the incidence rate in the exposed group that is attributable to the exposure. So we're going to take these two up here, and we're going to divide by the incidence in the exposed group, because that's the way we know a proportion operates. Okay? And then we're going to note certain aspects, and I want to begin to show those to you. Okay, now I'm introducing you to a specific problem, and this is a group and not a population calculation. Okay, to get attributable risk, absolute risk or incidence rate, and this is for a prospective study, so you have memorized all of these cells and know what they mean and how to label them, because you're going to label them different when you do an odds ratio. Okay, so we have a group of healthy smokers and healthy non-smokers, and those that developed coronary heart disease was 84 over 3,000, which was 28. Okay, so the absolute risk is 28 per thousand, okay, for healthy smokers. The absolute risk for healthy non-smokers is 87 divided by 5,000, which is 17.4 per 1,000. Okay, now I want to show you how I did the calculations. Okay, there they are. That's just what I've told you. Now you could change this from incidence rate among exposed or incidence rate among non-exposed to absolute risk. That's the absolute risk. So we can in fact, I'm just going to make a modification, and excuse me, that's how we would do it. So we want to know the incidence rate or the absolute risk in the exposed group attributed to the exposure of smoking. So what we do is we just subtract the absolute risk in among healthy smokers from absolute risk among healthy non-smokers, and it's 10.6 per thousand per year. Now, what's the proportion of total incidence or the incidence rate in the exposed group attributable to the exposure? So the same thing, we go the same way, and we're going to come out with a percentage in this particular case, and that I didn't emphasize before, but you know it's a proportion, so you know it's going to be expressed as a percentage. Now notice a proportion that if they didn't engage in the behavior, what it would do. Okay, so 37.9% denotes a morbidity from coronary heart disease among smokers. There would be, and here's the key, and you hear this on the radio all the time. If you listen to study results, if you're driving through Indianapolis or other big cities, or sometimes on national news, you'll hear the same information, and they won't go into some of the more nitty-gritty details, but they often will report this, and they would indicate there would be a 37.9 reduction in the incidence rate of coronary heart disease if smoking were eliminated. Now I'd like to introduce you to a specific problem related to a prospective or longitudinal study. And again, I want you to focus on the layout of the table as I mentioned before, and I want to go slow through this so you're not lost, and I'll show you how I do my calculations, and they're not difficult. But if we were going to come up with absolute risk, we'd divide 84 by 3,000, and it would be 28.0 per thousand per year. And if we were going to do absolute risk for healthy non-smokers, it would be 87 divided by 5,000, or 17.4 per thousand per year. Now, here's my calculations. And I'll show you how I came up with those answers. Okay, so you ought to be able to replicate that, and it's always the same. So, and if you want to make it more complete, you can put another slash and put year on the end, as it's shown in the next one. Now I want to talk about attributable risks, the amount of risk attributable to engaging in the behavior. Okay, so we have incidence rate or absolute risk in the exposed group that's attributable to the exposure or smoking. So the additional or the risks that you take, or anyone in your family takes, or your friends take when they smoke, according to this data, is 10.6 per thousand per year. Okay, and we'll talk more about these so you can translate them, and you know that risk is relative to a population, and that this is a hypothetical population. So you can say, well, if we had a hypothetical group of 1,000, 10.6 would be at risk if they smoked. Okay, now We look at the proportion of total absolute risk in an exposed group attributable to the exposure. And again, we've used a proportion. It's reported as a percentage. That's why I prefer the word proportion, as I mentioned before. You can see the calculations, not too difficult. And the 37.9 denotes the morbidity from coronary heart disease among smokers. There would be a 37.9% reduction in incidence, the incidence rate of coronary heart disease if smoking were eliminated. Okay, now, this is a statistic you often hear on the radio or on television, or when they're trying to promote the results of a study and telling you the benefits of it. And so proportion of attributable risk is one that you hear a lot, along with relative risk. And we haven't covered relative risk, and it's the main one, it's the main statistic that you will hear most often. Okay? So we've covered most of those calculations, but we'll get to relative risk here in just a minute. Now, the most difficult for people is attributable risk, and I don't really understand why, but whether I do or I don't doesn't make any difference. It's whether you understand why. So if you look, I'm going to go through this. This is the amount of risk in that we calculated, or the absolute risk. And the absolute risk in the exposed group was 28.0, right? So you can just put 28.0 here. And then the amount in the unexposed group was 17.4, and you can put that there. Now, if you subtract, which we're going to do, this is the unexposed group, and this is the number of people who are going to become ill even though they didn't smoke. They're going to develop lung cancer even though they didn't smoke. And so we're going to subtract these two, and this is the attributable risk to smoking right here, not this. This is the baseline amount. So what is the amount of attributed to the condition or disease? That would be this amount, or 10.6, right? Because we subtracted this 17.4 from 28.0, and so we came up with 10.6, and that was the attributable risk per 1,000 per year. So this is the amount attributed to engaging in smoking. Okay? Now I hope that's clear, and that you don't have any trouble comprehending what we're trying to mean by attributable risk. I know when I first learned this, once I saw the diagram, I understood exactly what attributable risk meant. And if you think about the line listing for the foodborne outbreak, you can see that some people don't get sick, and some people do. Okay, so this is these people have gotten sick, and we subtracted them out. Okay. Now, I told you there was, with the prospective study, there was group statistics and there were population statistics. And we have to obtain data from a secondary source to do population statistics. And I want you to go through this carefully with me so you understand it. This data came from healthy people 2020. We could have used other sources from the U.S. Department, which is from the U.S. Department of Health and Human Services, or we could have used other sources such as Back to the Future, which is a research group at the University of Michigan who has looked at all kinds of health risk behaviors for a long time, including smoking. All right? So, what we're trying to do here is we're trying to see, we used a group from Purdue that we selected previously. We used a group of students, so now we're trying to determine, do these group of students or people that we have selected really represent the nation at large, or is there something peculiar about them? Okay? Now, if we look at population statistics, which I think this is pretty interesting in terms of the percentage of people who smoke and whether it's changed a lot over the years, and you can see that the the percentage who smoke in the total population is 20.6 in 2008, 20.6 in 2009, 19.3 in 2010, and 19 even in 2011. So if I was going to ask you about a trend, that's a linear line, isn't it? There's little variation in the percentage of people who smoke. In other words, you could tell me, well, 1 out of 5 people in America smoke. That would be a simple way to say it. And then you could go down and you can say, well, who smokes the most? If we look at race, ethnicity, which is an important factor, who amongst these groups smokes the most or who smokes the least? Now let's look at this is really interesting for Asians. They tend to smoke the least, and it hasn't changed. Looks like there was a little spike, and this is probably an anomaly. I would have a question about why we got a higher value in 2009 than we did in any of the other years. Okay, and the DSU indicates that the data is statistically unreliable, and that's why they didn't include it. Now, let's go down and look at Black or African American only, and you can see their smoking rates. And there's a slight drop, but it's not a major drop. And you can see that probably you would conclude that black and whites smoke just about the same amount. We're going to continue with the table. I just wanted to point out a couple of other things to you, that you can see that the target in 2020 is 12%, and that seems ambitious according to these data. But if we were going to, and I want to get back because we are talking about population groups, I want to talk to you about the values that I'm going to be using in this population problem. So, but I did want to reflect on this table because I think it's pretty telling. And you can see by looking at the table that, let's just take the last year, that if you're looking at educational attainment, that the lower the education, the greater percentage of smokers. So if you have an advanced degree, you can see that it's very unlikely that you're going to smoke. Doesn't mean that you won't, but it's unlikely. And family income, the more you're under the poverty level, you're going to smoke. And so we draw conclusions pretty quickly. We can see that if if you're a low income person, if you're not particularly educated, and that if you just look at the age aspects, we're going to see that those what 18, I guess it's a better indicator is 40. Well, my apologies to you here. This is doesn't give us very much information about age. Age doesn't seem to be really a contributing factor, but you can see the sex difference. So males still smoke more than females. But what's really interesting is what you note here. You notice a tremendous drop from after age 65. I'd like you to think as to why would this occur. And I wonder if you have any ideas. And what we note, or we come to appreciate and recognize, that smokers are dying after the age of 65, and that's what this data reflects. So, and then we could do it occupationally and look at the professions or the occupations where people smoke the most. Now, they do have a CI or confidence interval of 95%. So if they were going to draw this data, a sample of this data, 95 times out of 100, they come up with the same value. So we have pretty good confidence that this data is important. Now, the number that we're going to be using for our problem is going to be the total population, or the percentage of smokers, which is 19%. So going on to the next slide, we're going to calculate the population statistics, because we've already done the group statistics, and this is not nearly as difficult as what it seems. So you just flow with me, and I think you'll find that things go together rather nicely. But we're going to calculate the attributable risks for the exposed group, attributable risks for the population taken from a secondary source. So we know that 19%. We know that 19% came from a secondary source, and that happened to be from the CDC. And attributable risk in the population which is due to exposure can be calculated by subtracting incidence in the population and incidence in the non-exposed group. Okay, now this is, notice the word population, because we're going to be using values here from the population to calculate incidence rate, and we're going to use values here, and you'll see very quickly, but we're going to use group data for the comparison group. So to calculate, you must either know the incidence rate and the total population, or the incidence rate among smokers, or the incidence rate among non-smokers, and the proportion of the total population that smokes from which the incidence rate in the exposed group can be calculated. Well, we know this, right? This is what we got from the secondary source, and we talked about where we can get this information. We went over that table pretty thoroughly, and you can go back and look at it. And based on the current population, or our current information, I should say, we really do know all of this. We know the incidence among smokers in our group is 28 per thousand per year. We know the incidence of non-smokers from our data is this, and the proportion is 19% as denoted in the Healthy People 2020 document. Now let's watch what happens to this data to make adjustments to see whether our group really represents the population or not. Okay, assume from this secondary source of information that the proportion of smokers in a population is 19% and 81% for non-smokers. Well, you say, where do we get the 81%? Well, if 19% smoke, we're going to subtract that from 100%, and that would leave us 81% who didn't smoke. Okay, so that's simply where that value comes from. Now, notice how we substitute the numbers in. We substitute the 19% in. We're going to do a calculation. We're going to multiply it. And this is our group data. And we're going to take the non-smokers and we're going to multiply it by this factor, and we're going to add these two together because we're going to use this value in our calculation. Okay? Next, what happens, we ask what the attributable risk is for the incidence in the total population and incidence in the non-exposed group, and here's what we have. Excuse me. We've done the multiplication, and here's the value. This value is being shifted and used here. We're always going to take the non-smokers and use them as a secondary value. So the attributable risk in the problem is 2.0. Okay, now you may realize before that the attributable risk was 10.6, so it's dropped quite a bit. So we are beginning to wonder at this point, we're thinking to ourselves, well, maybe the population, or the group sampling procedures, or the group that we used and then we sampled from, is not a very representative group. Now let's just go on and we'll do the other calculations, and you know this, it's the same, except we're going to look at the incidence rate in the total population and the incidence rate in the non-exposed group. So we're going to use this value here, we're going to use this value here, and we're going to again use this value here. Just check me out and see whether I'm correct. Okay. So instead of 37.9, we have 10.3. So there should be a total reduction of 10.3% in the incidence rate of coronary heart disease in this population if smoking were eliminated. Well, that's a huge difference in terms of what we got before. So our sample is not very representative of these better data from the United States, all over the United States, in terms of the proportion or the percentage you smoke. Okay, now all we're doing is the same type of thing. Now notice I'm doing a group versus population comparison in terms of attributable risk. Okay, and this is always our baseline amount or our endemic state, and so when we take away that background, this was a group data, we had 10.6, right, per 1,000 per year. When we look at the population, we had 19.4 versus 17.4. We came up with 2, so the attributable risk was 2, and this was 10.6. So when we So we did the calculations here as we did the calculations here to come up with a 10.6, and we'd already done this. So the difference between the group and the population is 8.6. So that's a big difference in terms of attributable risk. That means you're less at risk by using the population information than you are the group information. We would believe and say that we would have more confidence and this would be a more valid score than this one, because this is based on the total U.S. population, where this is based on a small group of people. Okay, relative risk. We ask, is there an association between exposure and disease? If so, how strong is the association? And relative risk answers those questions. So if we look at it, and absolute risk, so you know that that's incidence rate among the exposed group, and absolute risk or incidence rate among the non-exposed group. It's a very simple statistic, right? There's nothing that's particularly complicated about it. It's just simple division. Okay? So, again, we have relative risk, and here's the formula for it. And in our problem, we could use, for the group, we would have a relative risk of 1 divided by the other, which would give us 1.60. Now let me interpret this for you. A 1 is a null hypothesis, which means there's no difference in risk. And since it's 1.61, we would say that just dropping the 1 off, that it's a 61% increase in risk over 1, or it's 1.61 more than the unexposed group. So you can talk about it in two different ways. You can say it's a 61% increase, or it's a 1.61 more or greater than the unexposed group. Okay? Now, when we look at this, this is how we look at values, and I want to take this slowly with you. If we get a value here, let's say this is 0.78, the relative risk is 0.78. That means it's a protective factor. That's a behavior that you ought to engage in. Let's say it's 0.54. That's something that you ought to do. And sometimes we find that the relative risk for exercise falls into these numbers under 1, or the null hypothesis. And if it's greater than 1, in this particular case, you're at risk. But we don't consider, generally what we consider a critical value for you really being at risk is 2, which means you're 2 times the risk for a particular risk factor. So you're double the risk. So that's another way to say it. An odds ratio, we use an odds ratio comes out with a score very similar to those that have been, well, identical to these scores that I'm reporting here, and you interpret it in the same way. Okay? And an odds ratio is a good estimate, a good estimate of relative risk, because we know the Cadillac, the best is from a prospective study. It says, when the cases studied are representative of all people with the disease in the population from which the cases were drawn with regard to the history of exposure, And we already talked about a group that we selected that wasn't very representative of the population. We just showed that. We went through that process. The control studied a representative of all people without the disease in the population from which the cases were drawn with regard to the history of the exposure. And the disease studied is infrequent. So when you're going to use an odds ratio is when the disease studied is infrequent. So when you're going to use a cross-sectional design, when you're going to use a case control study design, where you're going to use a historical perspective design, you use those when the disease being studied is infrequent. If it's a rare disease, you don't want to use a prospective study because it takes too long for the disease to develop and it's too expensive of a process. So I hope that is clear to you. Now, so here's just a little quick review for you. RR is calculated directly. It's a gold standard. RR cannot be calculated directly and can be termed relative odds, although we don't calculate relative odds for a prospective study, not when you have the gold standard of relative risk. So with an odds ratio, which an odds ratio is an estimate of relative risk, and we designate this as OR versus RR. So, and I'll show you in a minute that this is just a multiplication of cross products and is used again as an estimate of relative risk. But this would be designated OR versus RR. And we do not calculate relative odds, which we could, and I'll show you relative odds would be calculated the way we calculate an odds ratio. Okay, I told you that there was 3 tables that you needed to know, that you needed to take a snapshot from. And this is an odds ratio for an unmatched design. In other words, we're drawing people at random and they go into one group or another, and so we're not trying to match people on a set of demographic variables and then to do our statistics based on them, and I'll cover that so you know it, okay? Now, so you obtain an odds ratio from a case control, historical perspective, or cross-sectional study. And an odds ratio is the multiplication of cross products, okay, divided by the multiplication of those cross products. That's an odds ratio. And you know relative risk is not calculated this way. Okay, so let's look at the next slide. Okay, this shows, and I want you to notice the layout of the table again. Cases with the disease, controls without the disease, were exposed, were not exposed, and the multiplication of cross products. And this is how we calculate an odds ratio for unmatched pairs. Okay? So I want you to be certain to notice the headings in comparison to the prior table for relative risk. Note that the proportion of exposed in the lower left corner, which is really focusing indirectly on attributable risk. But normally you don't see it, normally you don't calculate it, you only calculate one value for a case control study of unmatched pairs. Okay? So let's try this together. Now notice this layout of the table. the total really is in the wrong place. It should be the total here. This is just to sort of confuse you a little bit, and because I don't want you to get used to looking at values in a certain place and thinking that you ought to be using these values in the multiplication of cross products. That would not be appropriate. So we'd probably move the total down here. Now, first select cases with coronary heart disease and controls. Then determine past exposure to smoking. And then you would do next a multiplication of cross products. And notice this is how it's done. And the multiplication and the division. And the odds ratio is 1.62. Now you interpret that 1.62 the same way we did for relative risk. There's no difference in that. There's no difference in that interpretation. So it's an estimate of relative risk. And we talked about when it is a good estimate. And this study is much less expensive than a prospective longitudinal study. And but otherwise you only get one statistic from it. You don't get four like you did from the prospective study. Okay, and I want you to notice that we have cases and controls. So this is a case control study, and then we determine based on the past exposure to smoking and non-smoking by looking at medical records or by some particular means to determine whether they're a smoker or a non-smoker. Now let me add one other thing that's important that often is overlooked. We want to take the exposed group should be those who have the highest exposure, and the non-exposed group or unexposed group would have the least exposure. So if we could take people who smoked 3 packs of cigarettes or 60 cigarettes a day and compare those who don't smoke at all, that's what we want to do. We don't want to do the least comparison first. We don't want to take a group that only smokes 1 pack and compare them to those who do not smoke any cigarettes. What we're trying to do is we're trying to determine whether there is an association. And so if the association is likely to occur under the worst condition or the greatest smoking frequency. Okay, and that's an important point to remember in all of this. And I don't want you to forget that, because that's just what goes on. Okay, what is the effect and what does it mean? Well, this number is greater than the null hypothesis, which is 1, right? And it's 0.62% increase. There's a 0.62% increase over the null hypothesis of 1, or a 1.62 or 1.62 more risk than the non-exposed group, or another way you could say it is a 161% higher risk than the controls. So you've got 3 ways that you can say that. All of them are correct, and you might familiarize yourself with those. So we can say it's a 62% increase risk over the null hypothesis of 1, or it's 1.62 more at risk than the non-exposed group, or we can say it's 1.62% higher risk than the controls. Okay, and notice how I've made every comparison in reference to the information on the table. Okay, so I've not gone outside um, um, the source of information that's presented here. Now, what does this mean? Well, this is not very much of a risk. We said anything over 2 was meaningful. Now, people said, that's double the risk. And people said, well, what is the highest value you've ever seen? The highest odds ratio or relative risk value I've ever seen is 16. And that's probably a behavior I would not engage in. That tells me that there's great risk, that there's substantial risk, and a behavior that would cause ill effects, is likely to cause ill effects to your health. Now, I couldn't go much further than that based on one study, but if 2 is bad, 16 is a lot worse than 2. Okay? And you could put it into the percentages and relationship to the null hypothesis, and go through the same process that I've done here, and you might want to do that just to see whether you could interpret the 16 in the ways that we've talked about thus far. Okay, next, calculating the odds ratio in a matched pairs case control studies. I want to read this to you. Controls are often selected by matching each control to a similar case based on common demographic variables plus other variables found in the research literature that are known to be important. Below are some of the variables that probably would be included in related to disease, and I share these with you. Okay? Sex, age, race, socioeconomic status, whatnot. Or, you could talk about devoutness in terms of religion, okay, or diet. 7-day Adventists were very important and brought a lot of information to us because they were vegetarians or vegans. I can't remember which, but that study's been done some time ago. Okay, so there's so I could match these subjects on, let me back up here. I could match these 2 subjects on, one would be a case, one would be a control, on sex, age, race, and socioeconomic status. Now, the more of these variables you take into account, the more difficult it is to find a control case, a control that is similar to the case that you're going to do the comparison against. So this just but you are taking these factors into account a priori and ruling them out because you think, based on the research literature or other reasons, that they may bias the findings if we don't match subjects, and therefore eliminate these variables as a source of bias or error. Okay? Now, what we're interested in is the discordant pairs, but let me cover the concordant pairs. The concordant pairs in which both the case and the control were exposed. They're not going to tell us much in this case. Pairs in which neither the case nor the control was exposed. Okay? The discordant pairs, they're going to tell us what's wrong. They're the most important of the 2 sets of pairs. Pairs in which the case was exposed but the control was not. That's interesting. Pairs in which the control was exposed but the case was not. Okay? And again, when you're following an epidemiologic approach, you're organizing data into a 2 by 2 contingency table, A, B, C, D, as we have seen before. And we're interested in the pairs that don't get along. The first two pairs we used to call these lovers and these quarrelers. So if you want to think of a relationship, these folks get along, these folks don't, but these are the ones that are going to inform us about the degree of exposure and how big a problem it is. Okay? So now, this is so important. Study the layout of this table. Usually when we have a case control study, the case comes up here and the control slides over. Now, that was for an unmatched pairs design. Now, for a matched pairs design, the cases are located here, and the controls are located on the top. So we have diseased. This is the concordant pairs, and we have non-diseased and non-diseased, and this is a concordant pair because they get along, right? And then when we go to non-diseased and diseased, this is a discordant pair. And then when we go to diseased and non-diseased here, we have a discordant pair. So all we need for this calculation for a case control matched pairs design are the discordant pairs, and this is how you calculate the odds ratio in this particular case. Okay, and odds ratio in a matched pair study is based on only B and C are the arguers, those that don't get along, those that are discordant. Okay? Now, further, the concordant pairs I mentioned are A and D, and we ignore those. They're not going to provide us any information because they agree. And if we went further, the odds ratio for matched pairs is a ratio between the number of pairs in which a case was diseased and the control was not, B, divided by the number of pairs in which the control was diseased but the case was not. Okay, now I want to take you through a problem. Okay, let's see whether we can do this together. I want you to assume a study of cases and controls in which each control was matched to a case resulting in 10 pairs. Assume the following findings were E equals exposed and N equals non-exposed. So which ones are we going to be interested in? Well, this is a discordant pair, isn't it? And so we have exposed and non-exposed. So let's see. Let's just count these. So we would be interested in this. Let's not count them. Let's just look at, we'd be interested in this. This is a concordant pair. We're not interested in that. This is a concordant pair. We're not interested in that. This is a discordant pair. We're going to be interested in that. This is another discordant pair. We'll be interested in that. We won't be interested in this because they're a concordant pair. This is a discordant pair. This is a concordant pair, and this is a discordant pair, and this is a concordant pair. Okay, so let's count discordant pairs. Those are the ones we're after. So we got 1, right? We got 2, we have 3, and we have 4. Okay, so for cell B, we're going to have a 4. Now, we've got one other discordant pair. where the control does not agree with the case, and that's case number 5. So that is 1. Okay, so we only have one in which the case, in which the control doesn't agree with the case, and we have 5 cases that don't agree with the controls. So for our calculations, what we would do is we would fill out our cells. I didn't even bother to count the other ones because we're not interested in the concordant pairs. We're just interested in the discordant pairs. And this happens to give us an odds ratio of 4.0. So you can go through and read all of this to see why how you classify the others that have the same letters. Okay? So our odds ratio with a matched pairs is 4.0. Now, I want to show you something else, and that leads you to the reason that they're ignored. And we did our odds ratio with discordant pairs. But we could go on and do a case control unmatched. And I'm going to go back and show you how we're going to do this, okay? And you can go back and do it yourself. And we'll come back to this. Okay. Cases and controls in which we have exposure and non-exposure. So we have 1, 2, this is unmatched now. 1, 2, 3, 4, 5, 6. Okay? And that's going to go in cell A. So we got cases with the disease that are exposed. And then we got cases that are unexposed. 1, 2, 3, 4. And that's going to go in cell C. And then we got controls without the disease. Let's see, we got 1. Controls without the disease, we've got 1, 2, 3. Without the disease, or controls with the disease, exposed. We got 1, 2, 3, and we know there are 10, so we got, so this would go in cell B, the 1, 2, 3, and then we subtract that from 10 because we know there are 10 there. We would have 7 in. So 1, 2, 3, 4, 5, 6, 7, and those would be unexposed controls without the disease. Now let's go back over here. I want to show you what I've done. And this would be a case control unmatched study, and we would come up with results like that. If we did it that way, for the matched odds ratio, we would come up with a 4, and when you subtract the matched from the unmatched, it's 3.5. So we have gained 0.5 risk in terms of matched and doing a matched odds. In other words, let me go back, and I'll come back to this in a second. In other words, it tells us that these variables were very important to control because they had some influence on the degree of risk. And by controlling them and matching cases and controls, we gained a risk of 0.5, and because those were confounding variables, and the true risk, the risk we would report, is 4. And this would be a high risk because we said anything over 2 is substantial. So the suppression effect is how much influence the matching variables had on the odds ratio. If we use a few matching variables, we don't know which one had an effect, but one of them did have. and so we would have an interaction of those variables working together that would have greater risk. Okay, I think that concludes our statistics related to research designs, and the next topic I will introduce to you is causality.